Okay, so just the last little bit about this lecture. For this lecture is that well, from next lecture I'm going to talk a little bit of reduced space-based quantization and skip some of the details and tell you the results which are useful for your research. Uh, uh, and the details will be talked by Tony in the group meeting. So he will probably go into very much the computational details about reduced space-based quantization. Yeah, so I'm going to skip some of the details. But to this procedure is really contacting the research currently undergoing in our group, especially my recent work with Hong Guang and Haida Li. So all our recent work are based on this reduced space-based quantization, and we find this procedure is really promising and hopefully solving both problem 1 and problem 2 mentioned in this lecture. Okay, I think I should stop. And is there any questions?
I have a question.
Okay.
When you said M can be viewed as a self-adjoint operator, it is with this Friedrich extension, right?
That's right.
So I was wondering, with this extension, would the actual form of M gets changed?
No.
It gets complicated?
No. So the form is the same. So the expression of M is just the same. It's just it's a matter of domain of definition.
Okay.
Yeah. So Friedrich extension is a matter of domain of definition. So this is our. I mean, for any computation, it doesn't really affect any computation. So so this kind of extension is just a way of taking limit, right? I mean, in the infinite dimensional Hilbert space, it's, it is subtle to talk about limit. Yeah, I mean, when you talk about domain of definition, so firstly you define your operator on the dense domain, right? On the dense domain, and then you take the limit of this dense domain and to find the real domain. And usually the domain is some kind of closure of the dense domain where you actually define, where you originally define your operator. So here you define this master constraint operator on I mean, implicitly you define it on dense domain. What is this dense domain? This dense domain is just the states which are linear combination of spin networks, right? So first you have spin networks, a finite linear combination of spin network states give you a dense domain in the Hilbert space. And then when you take the limit, consider infinite linear combination of spin networks, and you get the entire Hilbert space, right? So originally, when you write down this operator, it means that it acts on linear combination, finite linear combination of spin networks, and this operator is well defined on that. And then you need to make certain closure of this domain to understand that some states which are not finite linear combinations, but infinite number of infinite linear combination of spin networks, but still it can be acted by master constraint. And some of the infinite linear combination, when you act on master constraint, you get infinity. It's not good because master constraint is unbounded operator. You cannot define on the entire Hilbert space. Yeah. So which means you need to find the boundary between some states which are still infinite linear combination of spin networks, which are still can be can be acted by the master constraint. But some of the states, when you act on master constraint, you get infinity. Yeah, it's outside domain of definition. You need to really find the exact boundary exact boundary of the domain of definition for the master constraint. And then this Friedrich extension just tell you what kind of boundary you can find. Yeah, so that your master constraint is well defined inside this boundary, inside the domain of definition, and in that domain, the master constraint is self-adjoint. Yeah. But
Okay.
when you actually do computation, because you just compute spin networks. For example, you compute matrix elements,
Yeah.
spin networks, right?
Yes.
So it doesn't really affect your computation.
Okay, great.
Yeah. Okay, so is there any other question? Okay, so if there's no other questions, so let's stop and see you